Mrs. Jasmine Mystica, Department of EC, St. Joseph's College of Engineering. I am teaching Advanced Real-Time Operating Systems for 6th semester students. As a part of the curriculum, we have included this QNX operating system after the QNX Everywhere program, where globally the operating system is now available for students of colleges, some recognized colleges, where the students take up the course, both theory and hands-on, through the span of 6 months to graduate on this course. So here, this lecture, we are covering some basics about the operating system, and also we are looking into one hands-on session where the process creation and management is being demonstrated. So first, before starting with QNX, we will learn the difference between what is a monolithic kernel and what is a microkernel. So a monolithic kernel, a very good example, is a Windows operating system, wherein most of the functionalities are put together into a single kernel space. So here you can see the diagram of a monolithic kernel, wherein scheduler, memory manager, network stack, serial driver, disk drivers, file system are all put together into a single package called the kernel space. Outside the kernel space is the user interface, which is the GUI, and also the application processes. So this type of kernel is typically being used in general purpose computers, where there is a lot of computation resources and storage resources available. However, this operating system is not suitable for anything of a smaller dimension. Say for example, considering an embedded system which has several requirements in terms of, which is constrained requirements in terms of memory space, execution time, and several other modalities, this kind of monolithic operating system with a larger kernel space is not suitable. So as a replacement to adapt an OS-based system design into embedded systems, the microkernel architecture emerged. So first here we can see, looking back into the monolithic kernels. So monolithic kernel, since the kernel footprint is larger, so it will make any driver development, or for that matter any debugging, very complex. So any applications that run in this larger space will obviously not be able to meet the real-time requirements. Also, when the kernel space is reduced, what will be the advantages? Obviously, the first advantage is the modularity. So when it comes to a smaller space, things are very close, and we can create isolated processes handling different tasks, and also certain amount of flexibility to the system design, wherein you can deploy a team working on different processes separately. So modularity and flexibility, also the high performance in terms of real-time operation are the added advantage when we migrate from such a monolithic kernel into a microkernel environment. So undoubtedly QNX, which is from BlackBerry, this operating system is also having a microkernel architecture. The opposite to monolithic is a microkernel, and our QNX is having a microkernel architecture. Now what is a microkernel? A microkernel is typically a smaller kernel footprint which does only the bare minimal essential functionality, and here you can see a microkernel, and most of the other functionality like the network stack, the drivers are all pulled out of the kernel space, and they are existing here as individual independent processes. So here you can see in the QNX operating system, there are two entities, the microkernel and the process manager. They are put together into a single package called the proc NTO. Now this proc NTO, now this is the essential the microkernel design. Any QNX application would actually call any application process would be managed by the QNX process manager and which is closely tied to the kernel. So this architecture kind of speeds up several activities, like whenever there is some need to communicate between two processes, say process X and process Y are two application processes which needs to communicate with one another. In that case, since this process manager is the responsible entity for handling this application, communication between the two application processes. Now the rate or the speed at which it will occur, how close it is tied to the kernel, you can see the interaction between processes are seamlessly robust compared to like this architecture, proc NTO, that is microkernel plus process manager put together will obviously speed up things like IPC. So this is one of the advantage of the QNX operating system. So here, looking at the diagram once again, so there are several drivers you can see which are all independent user space processes. They are not existing inside the kernel space, I repeat, they are present outside the kernel space as independent processes. And or you know that when there are multiple processes, say for example, let me clarify what is a process basically. Say considering a Windows operating system, there are multiple processes by meaning. We have, say for example, Chrome, we have MS Word, we have MS Paint, all these are typically processes. And sometimes there is a requirement, like say for example, you are copying an image from one file to another file, say from Excel to Word. So all this is like you're communicating between one process to another process. So this is the idea of a process typically. So this is in a general purpose system, whereas coming to embedded systems, we will see an example of what is a process in the upcoming slides. So here we can see there is this inter-process communication. For now, what is inter-process communication? Is simply communication between two processes. Process X, process Y communicating with one another. Now that is called inter-process communication. And this is the architecture where the independent user processes can communicate with one another, and since most of the services are running outside the kernel, fault isolation is very strong. What that is meaning, if there is any faulty process, the diagnosis is much faster compared to the monolithic architecture. Also, like it is more modular and flexible as we saw in the earlier slide. And overall, what is the advantage of having such an architecture where there is a separation between the user space and the kernel space, and most of the services are present outside the kernel space? The main advantage is it is more reliable, and it is like the maintainability is better compared to putting everything into a single box and like messing up things. There is a very clear separation, and as I said, the inter-process communication overhead, say process X communicating to process Y, the time taken for this communications to complete is robust, it is reduced. So the proc NTO architecture, we will see it in much detail. So the proc NTO consists of two main components basically. You can see the earlier diagram, taking a part of the diagram there. So it is the kernel and the process manager. So the kernel is typically the very essential, crucial part of the operating system, and it is accessed through something called kernel calls. Kernel calls are nothing but these are all a collection of programs. A kernel is typically a collection of programs, and these programs can be accessed by calling the particular function that is available within the kernel space. And it also handles threads and IPs. So any process communicating, say process X communicating to process Y, now that is being handled through the kernel. The kernel intervenes. The kernel is the middleman who is actually responsible for the communication. And coming to the process manager is itself, it is a process first, and it is having the process ID 1. So this you can see, the proc NTO, it itself is a process and it is having the process ID 1. Process, any process is a program that is loaded into the memory, that is actually capable of running. It's called as process. So here we can see the proc NTO itself is a process and it is having the process ID, which is like every process has an ID. And here the process ID for proc NTO is 1 in a QNX system. And there is this process manager. You can see it manages processes like basically all the application processes. It intervenes in the operation, also the communication and communication like message passing. There are several communication methods which like message passing, we have a shared memory communication. There are several methods which we will discuss in the future lectures. So it kind of governs any communication of process X to process Y. Everything is governed through this entity called proc NTO. And this proc NTO is the first process having PID 1. So what is a process? So before starting with understanding how the architecture, how everything comes together, we should know what is a process in itself. A single process is basically a program that is loaded into the memory, and every process is identified by an ID. As I said, proc NTO itself is a process having process ID 1. And here we can see a single process put together here, and every process, like when I say a program to run needs certain resources. So what are the resources? The resources are typically memory, and sometimes we can say in terms of files that are needed for the process to complete execution, and there are several other hardware requirements like a timer or something. So all these are the resources that are needed by a process. So a process is a program that is loaded into the memory, and there are several resources that is essential for a process to run to completion. So in the security context, you can see every process has ID and every process has certain set of abilities, so which is configurable in a QNX operating system. Like how we have in a Windows system, we have users and privileges. Similarly, in an embedded system, we have several processes. Each process is having an ID, and every process has a set of resources like memory, files, hardware requirements like timers, etc. Also, every process has its own abilities, like whether it is restricted to process, restricted to a particular application, or whether it is able to call the kernel space. There are some attributes which are configurable with respect to the process. So resources owned by the process are typically protected from another process. So this is the idea. Like there is a process which owns a set of memory or code or files. All those resources are localized to that process. Now this is called process opacity, where the resources that are used by the process are known only to itself and not to any process that is existing outside the entity. So here we can see the several resources that is present in a process. So there are threads, you can see. Now we will see what is a thread in the next slide. So threads are single line execution of a program, and there are memory. There are certain resources like mutex, like those who are into this embedded RTOS will know what is a mutex. So it is for access control mechanism which is used to regulate access to some shared resource, and there is a channel. So suppose if there is some data need to be fetched into the process. Obviously, there should be some channel to communicate or send or receive data, and there are something called file descriptors, which are like what are the files that are localized to the again the resources marked with descriptor. So the resources owned by the process are protected. That is very important point to note here. The resources available for a process are isolated from the another process that is existing in QNX system. So what is a thread? Next, a thread is a single flow of execution. As I said, it is a single line of program, a single line of code, typically a single main function, or from point A to point B, like there is only a single line of execution. There is no multiple branches, you can see. There is a single line of code, and it is identified by a thread ID, like how every process had a process ID. Similarly, every thread has a thread ID, and it is commonly abbreviated as TID, and earlier process ID is given as PID. So thread ID is PID, and a thread has also has some set of attributes like priority, what is the scheduling algorithm, the register set, the CPU mask, and the signal mask. We will see all that like in the when we are specializing. And it is all attributes have to do with running the code. It's all its attributes. It is having like for running the code, what is the rule? Now that is what is the set of attributes corresponding to a thread. So processes and threads. Threads run in a process. So this is very fascinating. So you can see. Now this is a process, the circle, the sphere is a process. Inside we have a one thread, one single threaded process. And whereas the other process there on the to my left hand side, that process is having two threads. However, there are localized resources. You can see channel, mutex, memory, etc. being present here inside the process. However, one process has two threads and another process has one thread. The very important point to note here is any process should have minimum one thread. So there, however, there can be multiple threads in a single process, but any process should have minimum of one thread. So threads basically they run code, and process is the entity as the whole. It governs all the resources. This is the idea between process and a thread. So a thread is the code that is running, and a process is the larger entity which is typically you can say it owns all the resources that is necessary for the thread. And threads, we can say it runs in a process. So once again, the processes and threads are the building blocks in a QNX based system. So what do you mean by building blocks? That is, we stack one on the top of the other in order to create something functional. So such an entity is a process and a thread in a QNX based system. So a processes, like you can see, it is basically visible to each other. All the processes are visible, all the application processes are visible to one another. However, they can communicate with one another, but the resources of the process are localized. And the thread are the implementation details. What is a thread? Thread is just the code that is present inside the process. So we will see one good example where this can play out into a system. And here we can see an example of an assembly line. So assembly line is pretty much seen in any factory that is automated. And here we can see several different operations being held on different stages. So we can see a conveyor belt which is controlled by a conveyor motor. Say there are two drill bits, large drill, small drill, and there is a stamper, and the gadgets are being made on the belt. So this is a setup which is seen in most of the automated factories. Now where this process thread comes into play? So we can see the process that monitor and control these devices. There are several devices, as I said. Considering this as an autonomous system, we can use QNX and design an application on top of it. So first we can see there are several entities which are functional. We can see there is a motor, the drills and the stamper. These are the functional entities. Now when I am supposed to design a control system for this conveyor belt, I will go about seeing each of these functional entity as an individual or independent process. So all these, like the notation is back, right? The circular or the spherical notation indicates the process. So now are these the only processes? Are there only 5 processes into this complex system of managing the entire operations on top over a conveyor belt? Is it only 4 processes that we will program? No, not. There are layers of processes. You can see there will be more levels of processes that is being present. So here, considering the embedded system of the conveyor belt application, we have our key processes which are 2 drills, stamper and a motor, and on top of it is a line control process which kind of helps coordinating all the 4 processes. Also there is a logger process which maintains the data records, and there is also a user interface process which is communicating to the line control process. So this blue arrow indicates communication that is happening between the processes, and the blue spheres, they indicate the individual processes that are part of the system. Now process opacity. Now this is one very important point for any programmer to be aware of. One process should not be aware of the threads in another process. So this is a rule. So any resource, like I said, the resources of a process are localized to it. So is the thread. So the threads are the implementation detail of the process, and they are not open or available to any other process to access it. The resources can be shared, however, the threads are completely opaque. The thread that belongs to one process cannot be accessed by another process. So why such design is essential? So we have studied object-oriented design. So here I could say that the process is the object, and this makes the processes highly flexible and highly scalable and configurable. So we can see that dynamically we can use one thread, and or a process can use multiple threads, and it can be created and destroyed as and when needed by the process. The thread is like the execution of it is a single line of execution which can be created and destroyed as and when needed by the process. So this is giving more room for the flexibility, and scalable and configurability is better because of this process opacity is. If the clients and servers, say for example, there are 2 processes, process A, process B. One is a client process and the another is a server process. Let me say, the earlier example we saw, say for example, the user interface is a client process, the line control is a server process, for example. and just naming them as client and server, because UI would send or require data from the line control, right? So one of the process can be termed. Now this is just the terminology. Basically there are two processes X and Y, one of which can act as a server and the other can act as a client. So this is the idea of the terminology client and server. And it is that these processes, since they are opaque, I mean we can have since there are like several clients and several servers of a similar genre, for similar kind of sensors. So there are the two drills we saw earlier. So there can be a possibility that we can have a similar names for the threads, and it is completely fine since the threads are localized to the process and are opaque to outside any entity outside the process. We can reuse the names of the threads. And why this threaded architecture is essential? Why can't we simply have process, and why this thread is so very important in a QNX system? Some examples of multi-threaded process is here we can see when there is something very much time critical. Say for example, there are multiple processes that is existing. One of the process is doing a routine job. Say for example, we have a sensor and one process, say process A, it simply reads some information from the sensor, and there is a process B which does something very critical out of the value that is acquired from the sensor. So there are priority levels among, when I am talking about processes, the processes may come with priority levels when it is about an embedded system. So the higher priority time critical job can be handled separately on a thread, whereas the lower priority jobs are put together and another thread, or maybe so multiple threads, that does the less critical work. So this is the idea of having threads. So we can group based on priority the activities that needs time critical attention are classified and are handled separately. And pool of worker threads, yes. Now this is where when there are multiple threads, more threads, all of them busy handling their own tasks, and all these threads are still available for new requests. So the kernel, what it does, it can give a message to any of these threads, and like when you have multiple threads, a pool of threads, I mean collection of threads doing the same work, when one thread is busy carrying out the work, you can use a copy of it or something similar to it to do the work. By, let's say there is a backup, like you can have A, B, C, D all capable of doing the same job. A person can allocate the work to either A or B. If B is still busy with a task, you can go for C. So this is the idea of having multiple threads, or simply rather than a single entity called process, we have, like, in order to make things robust, in order to be more highly in order to have highly functional ability, high functionality, high potential, like high speed functionality, we can go for doing these tasks through threads. Rather than having a single entity doing the job, I will have several options to do the job. So this comes in handy, like mostly we can know that the embedded systems today are running on multi-core machines. So you know that there are several cores present in the hardware perspective. So what these threads can do is they can actually be using the multiple core, I mean the several cores can there is something called core affinity, where depending upon the nature of the task, the core is being allocated to the thread, and these are some advantages of having multiple threads in the QNX system. So we'll move to the next slide. Like before entering the next slide, we will just wind up this part 1 of the video.